So our next paper is Artificial Intelligence Embedded Image Process Based Fatigue Life Determination on Wire Ropes Subject to Bending Loads. And it's a paper by Mohsen Seyyedi, and unfortunately he's unable to be with us today, and Professor Lutfi Al-Sharif is going to do it justice, we hope, on his behalf.
Thank you, Richard.
Thank you.
Hello, everyone. Mr. Seyyedi, unfortunately, couldn't be with us, so I've been asked to do the presentation. Okay, so it's Mohsen Seyyedi. I think Mohsen Seyyedi is a master's student at the Istanbul Technical University. He did his thesis under Erdem İmrak, Professor Erdem İmrak in Turkey, and it's an interesting paper. What he's done is twofold. So he's actually building a setup for initiating cracks in ropes. So it's like an accelerated life test, and you start getting cracks in these ropes after a certain period of time. That's the first part of what he's done, which is very interesting, because let me actually show you the setup. That's the setup. And what this does, then he can actually put in various ropes in there, put them under an accelerated life test very, very fast. He can get cracks in them. He records the conditions under which these ropes, the strands obviously, have cracked, and then he can start understanding how fast do these ropes break, if there's a new rope design, and so on. So that's the first part of it. I'll talk about the second part in a minute. So what Mr. Seyyedi has done, then he wants to understand steel wire rope fatigue. Obviously, the most important factor is the sheave to rope diameter, which is 40:1, I think, required in America. It's the same, 40:1, yeah. Minimum. So minimum. So 40:1. Obviously, if you use a ratio less than 40:1, you're bending. There's too much bending on the rope as it goes round the sheave. So you get more breaks. And what's worse than single bending is, who knows? Reverse bending. So if you have an arrangement where you're bending this way and then you're bending this way, that's the worst. And you might get through a set of ropes in 18 months. I've seen them change 18 months changing a set of ropes because it's such a bad installation where you're reverse bending continuously. So, and also he believes that the tensile load, what stress is on the rope is a factor, and obviously the rope composition, what type of rope is it, and so on. These are the factors, the three factors that he's taken into consideration. Tensile load, he can change the tensile load in his setup. He can obviously change the rope diameter and sheave diameter in his setup, and obviously he can put different ropes in. The aim is actually that's the first part. So gathering comprehensive data set. He's basically generating the data. You remember yesterday we talked about data. He's generating the data himself. So he's not going to different sites and saying, give me damaged ropes. And I guess that must be very, very difficult to find enough damaged ropes to study. So he's generating the damage himself. The next step, and this is the second part of the project, he wants to use AI to automate the process of checking for strand breaks in the ropes, which obviously we do today manually. And you count the number of breaks in the strand ropes every meter or 2 meters, or every 10 meters, whatever. Obviously, this is a badly damaged one. Or have you seen these on sites? Seen that much damage? Yeah, that much damage, yeah. So this is a fascinating mechanism. I love these things. Remind you of Victorian engineering, Mickey Mouse engineering, and so on, but I could sit down and watch these for hours. It's my favorite pastime. They have cameras. So there are 2 cameras there, and I'm going to ask you a question because I don't know the answer to it. Maybe you can help me with the answer. There's a diverter sheave here. That's the main sheave. There's another sheave there. This is the actuator. So this is the motor that's actually initiating the cycles. And we'll see how it works. It has an eccentric mechanism. So it's a 3-bar mechanism. So there's a bar here, there's a second bar, there's the third bar, there's the pivot. So this actually will start going up and down. As it goes up and down, it pulls the rope up and down, and it initiates a bend. There are 4 high-speed cameras. Now, if you look here, I think the cameras are looking at the rope from the side, not from this side. And that's what I didn't understand, because I would have thought the brake would initiate here, and you would want the camera to look at it from this point. I don't know. That might be something someone can actually suggest the reason for. But I would have thought if the rope is actually bending this way, then you will see the brake here and you will see the brake here, rather than seeing the brake here or here. But I don't know. I mean, maybe Stefan can comment on that later on. So look at it again from a different point of view. So there's the diverter, the sheave, the diverter sheave, 250 millimeters, 400 and 400. I'm sure he can change those by either changing the sheave or changing the rope to change the ratio. Now, how do you change the tensile strength on the rope? You put weights here, very simply. As you put weights here, this becomes heavier. It pulls the whole pulley down, and you get more tension in the rope, which must be a factor. So the tension in the rope, the ratio, are factors. And this is the mechanism, the eccentric mechanism that actually, so you convert rotational movement to reciprocating movement. Opposite to a train, a steam train, where you convert a reciprocating movement into a rotation on the wheel. And this is it. You can just sit there and watch it for hours. It's so beautiful. So you can see rotational movement convert into reciprocal movement. You can see the angle of wrap. So he's decided a certain angle of wrap. I don't know if you probably can change it by pushing the diverter sheave. So you can get a larger angle of wrap or a smaller angle of wrap. You see these like these in IKEA. Has anyone seen this in IKEA where they test the chair? And it keeps on testing the chair, these elastic chairs which you sit on. And so that's the first stage. And that first stage can actually, you can use it to study ropes, breakage in ropes, what parameters, Warrington type or seal type, different ropes and the breakages and so on. The second part is the image processing system. Yesterday we talked about artificial intelligence. This is another application of artificial intelligence where obviously you need data, but there is an important point which I'll talk about today. So these cameras actually have 249 frames per second. So they're quite fast cameras as opposed to 50 or 60. It's a 2 megapixel resolution, which I guess resolution is important because the higher resolution you have, the easier it is to detect the breaks. And as you can see, what the AI system will do, once it detects a crack, it will actually place either a square, a rectangle, or a circle around it, so having detected the break in the strand. And these are different samples. You can see large numbers of breaks, so you can see here large numbers of breaks in the strands. And these are the different samples. This is the AI system. Now, this is called supervised learning. So we have supervised learning, unsupervised learning, and reinforcement learning. This is called supervised because we are supervising the training of the system by telling it the right answers. So once you feed it this image, you tell it that I know that this is a break, this is a break, this is not a break. And you keep on training. That's why it's called supervised. You have to supervise it and tell it what the right answer is during the period of training. So this is a form of supervised learning. Now, this is a very, very important point, 80%. One of the misconceptions that many people have about AI, you go to a client and he says, I want an AI system which doesn't give me any error. I want a 100% system. That's impossible. You have to accept a certain level of error. And maybe wording the question in a different way, you have to place a certain level of certainty. So if you want answers with a high level of certainty, then you will have to put a higher threshold, and then you will accept cases where the system says, I can't decide whether this is a break or not a break. But you will never get to a system which says, I'm giving you these answers with 100% certainty. Now, depending on where you set that threshold, you get more answers or less answers. So if you set the threshold, you say, I'm only going to accept results with 90% of certainty, then you will get fewer results. It'll tell you, I'm only certain to 90% of these breaks. These breaks, I'm not sure whether they are breaks or not. You have to live with that. That's the way you deal with AI. There is no such thing as a 100% accurate AI system. And you will have to decide the cost of a missed alarm and the cost of a missed event or a false alarm. So a false alarm when it says this is a break when it's not a break, and a miss when it actually misses a break and there is a break. And you have to decide what the cost of each is. The cost of a miss, what is it to you? The cost of a false alarm, what is it to you? And then you decide your threshold. And you say, I'm going to ask for a 95% accuracy, which means that you might miss a number of breaks. And this is the training is going on with this system, and you can see the system is actually identifying a crack by placing a square around it. These are some results. So what does this tell us? This is the actual broken wires. So we know that this sample had 30 breaks in it. It's not going to be able to detect all of them. So in this case, at a level of certainty of 80%, it detected only 24 of them. This is where you set the threshold and you get more answers or fewer answers. So if you're asking it, I want you to be 80% sure when you tell me there's a break, that there is a break. And when you put that threshold, you get 24. If you're saying I'm going to accept a lower level of certainty, and then I can go and send the technician or the serviceman to check it as a follow-up, then when we set that to 40%, we're getting more. And the error is 7%. We've missed 7%. Here we've missed 20%. If the missing of a strand is important to you, then you have to lower that threshold. This is a very, very important concept in AI generally and image processing. And you can see the same. For example, here we have, there's no difference by setting 80% or 40%, we're getting the same result. We've missed one. One strand has been missed in this sample. No misses here, more misses here, and so on. Now, this is actually the design of the experiment. So the design of the experiment has decided to put different payloads, 200 and 400. This is by putting different weights. So they put more weights, and you get a payload of 400, which will achieve different tensile tension in the rope. Machine speed. The machine speed, I'm not sure if it actually affects the results, because the machine speed will generate more breaks in a shorter period of time. This is where the motor, the synchronous motor, was rotating at a faster speed or lower speed. So he's used here 40 RPM and 80 RPM. This is important. Obviously, this is the sheave to rope ratio. And I've used 50. And you would expect, obviously, you'd get more breaks in this case, and you'd get fewer breaks in this case. So, and then you can assess what is the effect of a rope to sheave ratio on the number of broken strands. And this is obviously the diameter of the ropes. And here he's using Warrington and different rope arrangements. So to conclude, 24 experiments were performed. So this is the first part of the setup, where before we get to an AI system, he's studying he's causing breaks and understanding the effect of these on the effect of the various parameters on the breaks. What he's suggesting as well is this is not just for this could be reverse engineered back to the design of ropes. So whoever is designing the rope can actually use this data usefully to go back and understand the design of the rope and the maintenance procedures. So that's these 3 points are the first part of the paper, or the thesis. The second part, he's actually gone on to the AI system and how you can automate the process. So he would envisage to actually placing cameras in the shaft or in the machine room, pointing at the rope, maybe with a certain level of lighting, obviously, to be able to automatically detect the breaks in the strand. He's also suggesting something interesting here, and I don't know if this has been done. I don't know, Rory might know. Placing strain gauges on the ropes. Can you do that? You can actually fit a strain gauge on the rope itself. And okay. So he's suggesting that further work could actually involve fitting a strain gauge, and I guess maybe the strain gauge can actually detect, as you break more strands, you get more elongation. So strain gauges could be a trigger to tell you, because you've broken so many strands, the elongation has become, because strain gauges could measure micrometers or less than a millimeter. So I found it very interesting. I only had a look yesterday, but I think it's an interesting piece of work. It's a pity that Mr. Seyyedi can't be with us today. But actually, I think this leads on to a more philosophical point as well. As we go on, and this is accelerating all the time, more and more of these tasks will become automated. So now you can have cameras in city centers which can detect crowd movements, burglaries on shops. It can obviously detect cars. It can detect suspicious behavior and so on. And what some cities are doing, they can actually get a video, a 2-hour or an 8-hour video. The AI system can search through the video. It can actually put hypertext or metadata, in text searchable metadata, onto the video. So it says minute 2 at 23 seconds, there was actually suspicious behavior in front of this shop. This car, for example, was moved and so on. This person moved from this place to this place. And obviously that is becoming more pervasive in our lives. And you will see, and this is obviously eventually will replace human beings. I know that's it's a philosophical, but it is an important subject that is happening on and more all the time. So I just had to finish on that note. Thank you very much.
Well done.
3 minutes.
Very good. Any questions or comments?
Okay, thank you. Thanks very much. That gives an overall idea. I read this paper before. So the method here is image processing. That's the first method. If you take strain gauges, you have a different type of signal. And that obviously would open some additional ways to detect the damage. Because, we are talking about the damage when the rope has got some wires broken. I'm not quite sure whether this method, image processing, would quantify how much damage has been done. That means before is at the border of...
It's too late.
Too late. So I think that's my suggestion would be to channel this work into this direction, because there's supervised learning. So therefore, there needs to be a specific number of samples which would enable to train the system. So before the system such as that is applied to detect in practice, you need to be trained. So there needs to be some repeatability.
Yes.
So that's my comments.
Yes.
Thank you.
I haven't seen strain. I mean, I know Rory said strain gauges. If you have data, I'll be interested to see what the strain gauges will look like.
Well, the strain should be the same. Okay, the remaining rope life is directly proportional to the speed of sound through the rope. But the strain gauge is going to show you that it's got the same load on it. If you're using it to measure load, so even if there's one strand left, it still have the same load.
I see. Okay. I was just going to say one other thing which might be interesting to people. The third type I mentioned was reinforcement learning. Reinforcement learning is a very, very interesting learning method, but it's actually the method which has been used to train AI in playing chess and the game Go. And it's fascinating because reinforcement learning, the machine can sit there. It has the rules. It knows the rules of chess or the game of Go. I don't know how to play Go. Does anyone know how to play Go here? But what it does, it sits there for hours, just generating games, new games, because it can play itself and learning. And that's how we got to, no human today can beat a chess game. And I think Go, that has been also broken with Go a couple of years ago, where no human can actually beat a machine in Go. So sad day, I think it's a sad day for humanity. I don't know, or happy day, I don't know. I think I get depressed sometimes the more I hear about things that AI can do to replace humans. Any other questions on? Okay, thank you very much, thank you.